Hi, welcome to Topological Methods for the Analysis of Data. In today's lecture, we're going to see how one can use persistence diagrams and other topological features in machine learning problems. Let's get started. Throughout the course, we've seen examples of how one can use barcodes or persistence diagrams to capture the overall shape and topology of your data set. So for example, here we have on the left-hand side a torus, or at least a point cloud sampled from a torus. And here we have on the right-hand side the barcodes computed from this data set. And then again, the idea is that one can use the barcodes to describe the shape of the data. Now, there are other situations where one has a data set where each data point has a shape of its own. So for example, in this data set from the paper Shape Retrieval for Non-Rigid 3D Human Models from 2014, we have a data set of different poses for 3 human subjects. So we have sort of a male, a female, and a baby, and they are all in different poses. And that is the data set. It's the collection of 3D meshes for several poses. And the goal is to classify the pose into the appropriate class. So again, in this case, each data point, right? So a data point is a shape. Each data point has sort of geometric and topological structure that one would like to leverage for the particular classification task. Another example of data where each data point has shape comes from computational chemistry. So the protein classification benchmark collection is a data set of proteins that one would like to classify. So here are 2 examples from that data set. And then if one would like to do protein classification, then one feature that can be used, or at least a set of features that can be used, is the overall shape in R3 that the protein has. So for example, here, I'm going to go ahead and show you persistence diagrams computed for these 2 models. So I've computed dimension 0 and 1, and as you can see, it is not the case that there are sort of salient topological features, right? There is no sort of point that is very far from the diagonal here in the persistence diagrams, but at least to the human eye, these 2 diagrams, the distribution of points looks different. So one idea that arises right away is to try to classify, again, geometric features or geometric objects by computing a geometric feature like a persistence diagram, and then trying to use the persistence diagrams to classify the original objects. So that's the methodology that we're going to explore throughout the lecture. The idea that one can start with raw data, which you then pre-process to have it in a clean format. So perhaps you had to do, data imputation to fix missing values, or you had to remove noise from the data, whatever you had to do to get it in a clean format. And then the first step after you have clean data that we're going to explore here is the idea of transforming it into data that is ready for applying TDA to it, right? So it's data that now has enough information that we can compute, for example, persistence diagrams, or we can compute Euler curves, or we can compute eigenvectors of the Laplacian. So this is data that is ready for the TDA methods that we have explored throughout the course. And then we apply these TDA methods. For example, we get persistence diagrams, right? And then once you have your persistence diagrams, you would like to use them for learning tasks. And the first idea that comes to mind is, how do I extract useful information from the persistence diagrams, which I can then use as features for classification and learning. So the first piece of the pipeline that we're going to explore is this question of transformers. What are some examples of things that one can do to clean data to turn it into TDA-ready data? So there are many standard things that one can do, dimensionality reduction being one of them. So in dimensionality reduction, the goal is to take a data that is complicated and perhaps express it with more informative features. So your data can be sort of high dimensional, and then the goal would be to embed it and recover it in a lower dimensional space. So isomap is one example of that. So for example, one of the steps in isomap is to compute an estimate of the geodesic distance along the data. So in particular, that gives you a better notion of sort of distance, or of geodesic distance between data points. Locally linear embeddings, or LLE, tries to explore sort of locally linear information of the data, and as does Hessian LLE, which is sort of an enhanced version of LLE. We also have Laplacian eigenmaps and diffusion geometry, which try to take into account sort of both geometry and density in the data. And then we have things like local PCA, which, much like LLE, tries to exploit locally linear information in the data set. So all of these methods and, all other standard dimensionality reduction pipelines allow you to take sort of data that may be high dimensional and complicated, and then turn it into sort of a lower dimensional representation where TDA methods can be sort of more successful, right? Because perhaps you have a better notion of distance, or because you have lower sort of noise that is not Hausdorff. Then another method that we have seen of how to turn clean data, or at least pre-processed data, into TDA-ready data is this idea of sliding windows and delay reconstructions. So this is a class of methods that we've observed are able to take data like time series, both sort of one-dimensional in things like video data, and then turn something that doesn't seem to have very clear topology or very clear shape into point clouds that do have shape, and whose shape reflects properties of the original time series. So one can use this idea of delay embeddings and sliding window reconstructions to turn time-varying data, or sort of sort of shape data, into something that has shape to it, and that one can explore via TDA methods. An alternative to doing sliding windows with the data that you're provided is to try to use sliding windows of community accepted features. So what is that? So the idea is to, instead of using the actual values from, let's say, the original time series, is to try and use values or features which are more informative in each window. So for example, in music, one can use things like timbral texture, which is a distinguishing factor between tones and the quality of sound. One can use things like Mel frequency and Sebstra coefficient, which is what sort of an imitation of what the human ear captures, and then things like chroma features that have to do with pitch. So all of these are different, at least for music. All of these are different community accepted features that one can use in lieu of the raw signal values. Let me give you an example of how this works. So for example, here we have a sort of signal, a sound recording. So here at the top left. So these are 3.5 seconds of a sound recording. So the raw signal is it's a high dimensional vector, so it's 153,000 dimensions more or less. And then what one can do is, in each piece of the signal, or at least each window, one can take summaries. So instead of the raw signal, one can compute things like timbre, as I said before, or these MFCC or chroma features. So these here in the bottom are two visualizations of sort of sliding windows across the signal. So sliding windows of the raw signal, and here's sliding windows of the features on the bottom right. And both of these visualizations are using PCA. And then what one can see using these community accepted features is that the sliding window sort of better traces out the different sort of regions within the song. So, you know, it goes from verses to bridges, transitions, and chorus, and it's a much sort of more informative visualization than what the raw signal would give you. So in summary, this idea of how to transform clean data into TDA-ready data, you know, there are many options, right? So one can do, again, things like dimensionality reduction to get, you know, better notions of distances, better notion of the sort of amelioration of noise. We can do things like sliding window embeddings to turn time series, for example, into point clouds. And then one can get creative. And for example, instead of using the raw signals, one can use community accepted features to do the sliding windows. And then, of course, your favorite method is also one that goes here. So going back to the pipeline, we now have at least an idea of how to go from raw data to clean data to TDA-ready data. What I want to focus on for the rest of the lecture is in this idea of how to perform sort of the bottom piece of the pipeline. In other words, how to take persistence diagrams, turn them into features, and then do classifications with them. So what I'll do now is I'll give you several examples in the literature of how this bottom piece of the pipeline has worked. So the first sort of method that I want to highlight is this idea of kernel methods, right? So kernel methods are very popular in data science, and what they try to do is to find ways of measuring similarity between data points. So the paper that I'm going to go over right now is a stable multi-scale kernel for topological machine learning. So this is from 2015. And then what is the idea? So imagine that you have a sequence of persistence diagrams, right? So you did something to your point cloud, to your original data set, turn it down now into a data set of persistence diagrams. So diagram 1, diagram 2, and all the way up to diagram n. So now you have a data set of persistence diagrams, and you would like to do learning with the diagrams. So if one had a way of constructing a kernel for persistence diagrams, and then what is a kernel is just a function k that is going to measure for each pair of diagrams, is going to give you a measure of how similar they are, right? So these, again, are kernels are sort of very prevalent in the data science literature. And then what you can do once you have sort of this kernel matrix or gram matrix, you can use methods like kernel SVM, kernel PCA, Gaussian processes, and just a myriad of tools that allow you to turn sort of a matrix measuring kernel similarities that then allow you to do things like classification and visualization. So the crux of the matter is how to define reasonable kernels for persistence diagrams. And then the proposal that this paper comes up with is by using something called scale space and by sort of analyzing a sort of heat equation, they come up with the following suggestion for a kernel between persistence diagrams. So here we have two persistence diagrams, DGM and DGM prime, right? So two persistence diagrams, and the kernel at scale sigma. So sigma is a positive real number. So the kernel between the diagram DGM and the kernel and the diagram DGM prime is given by the summation over all pairs of points a comma b in one of the diagrams and xy in the other diagram, and they just evaluate these two exponentials, right? So it's exponential using a comma b minus xy and then a comma b minus yx, right? So this gives you a notion of similarity between diagrams. It's a very simple formulation, but you know, there's some math that needs to be dealt with in order to get to an expression like this. So they apply their kernel to these synthetic data set of human poses. So using something called a heat kernel signature, it's not really important what this is right now, but what is interesting is to see what are the sort of classification accuracies that you get by using the sort of the proposed kernel, right? So this is this K sigma column, and they show that they get sort of pretty high accuracies in the task of classifying these human shapes. So that's one example of how kernel methods can be used in sort of for persistence diagrams, and again, especially when your data is comprised of objects which themselves have geometric and/or topological structure associated to them. Another type of methods used in machine learning for persistence diagrams comes from this paper, Persistent Homology Analysis of Brain Artery Trees. So this is a paper from a similar year. 2016 was the year that it was published. And let me go over what the idea is. So this paper belongs to a class of methods where one wants to sort of hand pick features from persistence diagrams. So the previous method, that of kernels, is sort of, again, one family of machine learning methods for persistence diagrams. And then this paper right here is an example of, you give me a family of persistence diagrams and I try to come up with a way, hopefully informed by the application, to hand pick features from the diagrams, right? So what is the problem? So imagine that you have sort of a collection of brain data, and what is the data is the sort of brain vasculature sort of each subject. And then the goal is to see how the shape of these sort of web of arteries correlates with measures like age and or gender. The idea being that, as people get older, the vasculature in their brains gets more and more complicated. So what is the idea? The idea is going to be to take this data set of brains and try to come up with persistent features or topological features that describe them. So the first step is to replace this picture of the data for point clouds that discretize them. So this is sort of a typical element in that data set. So what do? They compute two types of persistence diagrams. They compute zero-dimensional persistence by height, meaning that they look at the brains from bottom to top, and then they compute persistence diagrams by looking at the data by growth, and that is sort of the typical idea of growing balls around the data points. So for example, here there is the typical one-dimensional cycle that one would detect in the one-dimensional persistence diagrams. So what they do then is go through the process of feature extraction. So from each brain, they take the top 100 features which are more persistent. And this is just ranked by size. So this is what I meant by sort of hand-picking the features that you would like to use, right? So it's not that the algorithm is learning what are the features that one wants to extract from each persistence diagram, but rather that the data scientist decides that certain features are important. So here in this next slide is sort of the results of the analysis. So here's what they show. So they take the brains, compute persistence diagrams and select the features as I just described. Then they run just PCA on these features and select the first eigenvector. And then by projecting the sort of data onto, and by the data I mean the persistence features into this principal component, they get sort of the PC1 of the data. Okay, so this is PC1 of the persistent features from the brain data, and then the goal is to see how this correlates with age. So here in the plot on the right hand side, there is the age coordinate at the bottom, and then there is this PC1 score as the y coordinate. And then what they see is that the correlation of these two scores, of H and the PC1 score for persistence features, is higher than sort of any method used before this study. So the geometry of the brain vasculature really did correlate with H, which was the hypothesis, and the method described here was sort of much more effective at determining that than other methods. So this is the type of sort of hand-picked features that one can get, the types of results that one can get with hand-picked features. Another sort of type of methodology, which is a little bit more involved than hand-picking features, or at least perhaps let me say that it's more data-driven, in the sense that it is not picking features from the diagrams themselves, but turning the diagrams into something that can be fed into machine learning algorithms. So what is the idea of this paper, persistence images? So the method is actually pretty intuitive. So what is the idea? Start with a data set here on the left-hand side, and then from it compute persistence diagrams, in any way that you think is reasonable. This is a decision that the data scientist needs to make. So once you compute your diagram, then the goal, or at least one step one does in the middle, is to turn the diagram from the birth-death axis into the birth persistence axis, or the birth lifetime axis. So this is a transformation that is useful to turn sort of these sort of triangular diagrams into something that just looks square. It's just a bit easier to visualize, but these two representations have the same amount of information. So now the idea is to turn these diagrams into a surface. And there are several ways of doing that, but the idea would be to sort of put sort of bumps on top of each of the persistence points, and then the height of the bump is perhaps controlled by its persistence. So they turn the diagram into a surface and then discretize the surface at different levels of granularity to turn them into images. And now the idea is to use the resulting images in lieu of the persistence diagrams, which are just a collection of points. So just to summarize, taking data, computing the persistence diagrams, and then turning them into images, and then these image vectors can be used in learning tasks. So once you have images, of course, you can apply things like convolutional neural networks. And that is exactly what this paper right here does. TopologyNet, topology-based deep convolutional and multitask neural networks for biomolecular property predictions. So this computational biology paper explores the use of sort of featureization of persistence diagrams, images, and then using sort of convolutional neural networks for prediction. So here's the sort of visual perspective of what they're doing. The idea is to take topological fingerprints, like persistent images, and then use sort of the typical convolutional neural network architectures to train models. So in particular, they use these for molecular data or in the protein data, and the idea again is to turn sort of the proteins and the proteins that they observe into persistence diagrams, which are then turned into images fed through convolutional networks, which can then be used to predict things like globular protein mutation impacts and membrane protein mutation impacts. So the use of this type of methodology has actually led to pretty sort of good results in drug design. So they show that this topology net is at the top, meaning that they get the best mean squared errors of many methods that have come before. So again, the idea is to turn sort of this problem of protein classification, which again has, each protein itself has shape. You compute a persistence diagram for each molecule, or a family of persistence diagrams, and then turn them into things that a neural network can understand, for example, like an image. Here's another example of functional summaries from persistence diagrams that feel very much like images. So the study in question is topological and statistical behavior classifiers for tracking applications. So what is the problem, or at least one class of problems that are explored in this paper? So imagine that you're in the problem of tracking vehicles. So here are two vehicles. So, you have vehicle 1, which is in this light blue, and then you have vehicle 2, that is the path that a second driver is following. And then you would like to track sort of the vehicles using sensor data. And then you have sort of two profiles of driver, at least in this case. You have the normal driver in dark blue, and then you have the speeding driver in light blue. Okay, so just to show you some of the results. So this is what sort of a typical vehicle tracker does without the use of topological features. And I will explain in a moment what are the topological features that are included. So so what it says, what the tracker is saying is that, vehicle 1 starts here in dark blue, is going up, and then it goes to the left. And then the tracker realizes that it's following the wrong vehicle. So it actually goes back and says, no, the vehicle is actually going up. And then if you update it to the tracker with topological features, then it does, say that the vehicle is following the path that it's supposed to. Okay, so let me explain how these two pictures are generated, or at least what is the topological feature that is being added to sort of improve the behavior of the tracker. So the data in question comes from SUMO, a simulation of urban mobility. So essentially what it's doing is simulating vehicles of different behaviors driving around an urban environment. So there are two sort of profiles that one can detect for drivers. So a normal driver, if you look at his speed profile, is someone that sort of accelerates and then sort of stays at a constant speed, and then slows down. So it's someone that is driving conservatively. And then an erratic driver would be someone that, accelerates pretty quickly, but then he has to decelerate because he's going to perhaps avoid another vehicle, and then accelerates and decelerates. So this is what an erratic driver looks like. So here's one way in which one can turn these one-dimensional signals into persistence diagram features. So here are two one-dimensional signals on the left-hand side, one in red and the other one in black. And then the way we're going to generate persistence diagrams from them is by pairing local minima with local maxima of this function. So, or these functions rather. So the idea would be, let's say that you start at the bottom and you're sweeping up in the y-axis. Right? So as we sweep up, at some point we're going to find a local minima, for example, here in the black, and then we're going to record that event as a local minima appeared. So for example, as we continue to go up, the next local minima that we're going to find is right here in black as well. So we're going to record that event as a local minima appeared. Then at some point, we're going to continue to go up, and we're going to find that, again, another local minima has appeared, right? So we're going to record that event here, that a local minima appear. And then continuing up, at some point, we're going to record that this local maxima has appeared. And then this local maxima is connected to this local minima, and it's also connected to this local minima, right? There are no other local minima let's say next to it. Let's say next to it for now. And then we're going to use the elder rule to say that the class that was sort of born first is going to continue on, and then we're going to kill the class that was born sort of later, which is these local minima. So again, every time a local maxima appears, it is going to connect to local minima. So we mark it as such, and then as we continue to go up, we see that this local maxima appears, and then it is connecting sort of these local minima with this local minima, but this local minima was already paired, so we're going to kill that guy. Then this local minima appears, and so on. So this is a way of turning sort of local minima and maxima into a persistence diagram. And we see that if you have two functions, so one in black and one in red, then this pairing of local minima and maxima is going to be similar in terms of the bottleneck distance. So here are the two features that we get, right? So this is the speed profile of a normal driver. And again, we turn it into a persistence diagram by pairing local minima and local maxima. And this is the profile of an erratic driver, by pairing local minima and local maxima. And then again, we see that the diagrams are different. So what we do, or at least what the paper in question does, is they go through the following steps. The first thing is that they turn the persistence diagram into a collection of grids, right? So just like so imagine that you're turning a persistence diagram into an image. That is essentially the goal here. And then, look at persistence diagrams instead of birth death, meaning in the triangular way. We're going to look at them in the birth persistence way, so that is a square view instead of a diagonal view. And then we're going to just count the number of persistent pairs in each grid cell. Again, we're turning a persistence diagram into an image. So this here on the left is showing you the persistence diagrams that you get for the average non-aggressive driver. And then here on the right, you're looking at the average aggressive driver. So these, again, look like images that we can then use as vectors for machine learning applications. So in particular, they take the following data set to evaluate the performance of this featurization method. So what is the data set? The data set is the collection of beamed diagrams, meaning the images of speed profiles from the sumo-generated data set. So there are 100,000 training examples, 10,000 validation examples to choose parameters and such, and then 10,000 test samples to report accuracy. And then the classifier that is used is, for what driver profile you're getting, is a likelihood ratio test under logistic regression. So this is what happens again when you take a tracker, or at least the original tracker without the topological feature, is that the blue driver follows the blue path as it supposed to do. But then when it gets to the place where the two intersect, then you can get this conflation, that the two paths merge, and then the tracker gets confused and thinks that the normal driver is the one going to the left when it should be going up. But then when you add the topological feature, then you get the correct tracking. So this was an example where a system, an existing system, like a vehicle tracking system, was augmented by adding topological features. Another type of sort of machine learning application of topological features usually belongs to a different group of methods. And it's sort of represented by this paper. The paper in question is the ring of algebraic functions on persistence barcodes. And what it does is, instead of turning the persistence diagrams into images like we've seen before, or using kernel methods, the idea is to compute functional summaries from the persistence diagrams. Let me explain what I mean. So the idea is to generate features which are in a way informed by functions on persistence diagrams. So for example here, x, j, k, so j and k are just natural numbers. So x, j, k is going to be a function that for each diagram is going to produce a real number. And what is the real number in question is the summation over all the points in the persistence diagram. And what you're going to do is you're going to raise the birth time to the jth, you're going to raise the birth time to the k, and then you're going to multiply by the persistence. So this gives you a real number for each persistence diagram. And then what you do is you vary j and k. So in particular, for some choice of regime for j and k, you're getting a sequence of numbers for each diagram. So that's what I mean by a functional summary, is sort of giving you functions from the set of diagrams to the real numbers. And then the choice of these types of sort of polynomial features is most of the mathematics that this paper goes into, is explaining why this is a reasonable set of sort of functional features to choose from a mathematical perspective. Then the positive side of these features is that they vary continuously and consistently as the number of points change, right? So if you start to add points to the diagram slowly from the diagonal, sort of moving them up from the diagonal, then this is going to change continuously because of this factor. What is sort of debatable whether or not it is positive is that it sort of disproportionately sort of weights the value of points with high persistence. And there are now several examples where we've seen that the points that for classification tasks, the points that are far away from the diagonal are not necessarily the ones that carry most of the information. So this may be a positive or a negative depending on the application. So here is an example of how these features have been used in the literature. And this comes from a paper by Adcock, Rubin, and Carlsson, where they think about the problem of classification of hepatic lesions. So what is the data? The data is a collection of images and of lesions, and the goal is to classify what type of lesion is that you're looking at. So how do they produce barcodes from this data set of images? So the idea is the following. So for each image, take for example its grayscale values, right? So for example, here on the left, you have that this portion of the image is being numbered by the sort of grayscale value from 1, 2, 3, and so on. And then they're going to create a complex by saying, you know, we're going to add vertices and edges according to the values that we have here. So the ones are added first. So I add a vertex for each one, and then any two ones that are near each other are connected by an edge. Then the twos are then added, so vertices on all the twos, and then edges are added between the twos and the ones that are neighbors, and then the threes are added. And then what we do is we just compute the persistence of each one of these complexes and the barcodes as they change. So for example, here's the sort of 0 and 1 dimensional barcodes for these example. So they take these barcodes and then use a collection of features from the previous paper. So these sort of polynomial features, sort of the KLs features. And then with these sort of type of functional featurization, what they get is sort of classification results, you know, in the sort of 70s to 80s range. Then moving on from these sort of polynomial type of features, there is something that has been very popular in the literature, which is this idea of landscapes, persistence landscapes. So this is work of Peter Bubenik, again from 2015. And then what is the idea of persistence landscapes? And again, this is going to be another type of sort of functional summary for persistence diagrams. So the idea is, you know, start with a persistence diagram. In this case, the blue dots are going to be the points in the persistence diagram. And we're going to take a line connecting, you know, the diagonal to the point vertically, and then the point to the diagonal horizontally. And we do that for all the points in the persistence diagram. We're going to label the regions that are sort of resulting from these divisions. So the outer region, sort of outside of all the lines, is going to be labeled as 0. Now, going in, the first regions that we encounter, we're going to label them as 1 and 1. Again, we're going from the outside in. The next regions, we're going to call them 2 and 2. And then the next region, we're going to call them 3. Another way to think about this is as if we had sort of triangles. Maybe we turn these into a persistence birth kind of plot, and then what we're looking at is sort of these triangles, and they are sort of from the sort of back to the front, and we're numbering them from sort of their sort of outer boundaries. Okay, and that's exactly what sort of the next step is we look at these triangles, and then we sort of trace the outer boundaries going up and to the right, and then again up and to the right, and then again up and to the right. And then this collection of triangles is what is called landscapes. So just to give you an example of how this works, the idea is that if you have a bunch of diagrams that look like this, then it's going to give you a bunch of landscapes that look like that. So in particular, each diagram is giving you a collection of these sort of triangular functions, right? So for example, this diagram gave you 3 functions, and one can then turn these functions by, for example, evaluating them in some grid across these horizontal axes, to get a vector representation of each one of the functions. So here's an example of how this plays out. So here is a point cloud sampled from the torus, and also a point cloud sampled from the 2-dimensional sphere. And then for each shape, what is done in this paper is, you sample, let's say, 100 toroidal point clouds, you sample 100 spherical point clouds, and then for each one of them, you compute persistence diagrams and landscapes. So what is shown here is sort of the average landscape out of those 100 trials for each one of the shapes. So this is here the average landscape in dimension 0. This here in the middle is the average landscape in dimension 1, and here is the average landscape in dimension 2. And then the idea is that sort of the big picks are telling you sort of the big topological features in each one of these classes. Right, so the torus has these 2 features in dimension 1 and 1 feature in dimension 2. So hopefully that gives you a summary of this idea of going from persistence diagrams to features and then classification and learning. What I would like to do now is take another view of this problem, of the problem of classifying and doing regression with persistence diagrams, because thus far we've sort of shown examples of things like turn persistence diagrams into features. But I would like to take a sort of a more sort of principled approach to analyzing this box. So what is the sort of approach that I'm going to describe now? Is this idea of template functions. And again, the idea is to learn functions which for each diagram, let's say in my data set, can predict from them some value that we're interested in. Okay, so this can be, the class or a quantity that we want to predict. So what is the idea? So in typical machine learning, the picture is that we have, a data set, and perhaps we have 2 classes that we want to build a classifier for. So in here, our data set lives in, on the real line. So it's a 1-dimensional data set, something very simple. And then we have 2 classes, the blue spheres and the red crosses. And then we want to build a classifier that, can predict whether a new data point is either a blue dot or a cross. So in the end, what we want is a classifier, meaning a function from the real numbers, right? That, given a new point, can tell me what class it belongs to. So perhaps a classifier will look something like this, right? So it's going to be a function f from the reals to the reals. And then for values that are sort of very much to the left is perhaps going to output 0. And for values that are very much to the right is going to output, let's say, 1. And then for places in the middle, it is not so sure of whether it should be blue or red, but it does give you sort of a level of confidence as to what class you are, so that if a new data point appears, let's say this purple square, then the function can tell you, by evaluating it at that point, it can tell you sort of what class it is by giving you the value. So that's the typical idea of classification, sort of the pictorial, at least sort of depiction of what a classification problem looks like. In the end is, again, trying to learn a function from where your domain data set looks like, right? So if your data lives in R, then you're trying to learn a function from R to the real numbers, right? So it's learning functions. But now imagine that your data points are not red crosses or blue dots in the real numbers, but they're actually persistence diagrams. So for example, here I've overlaid a bunch of persistence diagrams, and then the color is indicating the class that the diagram belongs to, right? So if we want to do classification sort of in a methodical way, then we have to study the problem of learning functions on persistence diagrams. And that's what I want to try to communicate next. The idea of how to do classification by learning functions on the space of persistence diagrams. So what do I mean by the space of persistence diagrams? So a persistence diagram, as we've seen before, is something that looks like this. So one way to formalize it is by calling this region right here, the wedge, W, is going to be the collection of points in Euclidean space in R2, such that the x coordinate is non-negative and the y coordinate is bigger than x. So W is essentially the wedge that we have right here, right? So it's where the points in the persistence diagram usually live. So a persistence diagram is going to be comprised of two pieces of data. It's going to be a collection of points S, is a set inside the wedge, and then it's a function mu that is telling you how many times that point is repeated, the multiplicity function. And we're going to take D0 to be the collection of all the diagrams that you can obtain by putting finitely many points in here. So that's the set of all the finite persistence diagrams. And then there is a sort of a technical consideration, which is taking something called the metric completion with respect to the bottleneck distance. So this is just a mathematical construction that allows you to take limits. So now you can think about sequences and the limits of sequences in the space of persistence diagrams. So if this doesn't make sense to you, just think that D, script D, is just a collection of all the persistence diagrams that we're interested in. And then in here, we can think of processes like taking limits. So what is the problem at hand is given an arbitrary continuous functions, and this would be sort of the classifier that we're trying to learn. Let's say if we had a collection of sort of, for example, red diagrams and blue diagrams, and we want to find a function that classifies them. So this is the ground truth that we want to learn, and we want to approximate it arbitrarily well, given, for example, labeled data. So that's the problem. So template functions give you a way of approaching this problem. And what is the idea? So a template is just a function from the wedge, W, to the real numbers, which is continuous. And then we're also going to ask that the function has compact support containing W. All of that to mean that if you look at the places where the function f is not 0, then it has to be some closed region within the wedge, right? So for example, in blue here, I'm drawing the support of a typical template, So again, a template is just a continuous function from W to the real numbers, so that if you look at the places where it is not 0, then it's just some closed region, so some region that you can sort of put here in sort of inside the wedge. Okay, so the remark is that the following function, nu f, which is going to take a diagram, and what it's going to do is it's going to take all the points in the persistence diagram DGM, and it's going to take their values evaluated on f, on your template f, and then it's going to add these values, right? So this gives you a continuous function from D to R, right? So again, each diagram in here, you plug it in to this formula and it gives you a number. So each template is giving you sort of a functional feature for persistence diagrams. And then the remark is that doing this gives you a continuous function from persistence diagrams to the real numbers, so a continuous feature. Another way to think about these features is as if you were taking sort of an integral. So for the ones that know calculus, what I'm doing here is essentially integrating my function f, my template f, against a measure that one can associate to the diagram. Namely, we're putting sort of delta masses on each point, and then that gives you a measure, and then by integrating against that measure, you get sort of this value. But if this doesn't make sense to you, just think of it as each diagram is being evaluated on the points. The template function is being evaluated in all the points of the diagram, and then we're going to add up all those numbers. So here's an example of what a template function can look like. So something very simple. So for example, we can start by dividing the wedge into grids. And then for each grid point, we're going to put a function that is 1 at that grid point, and then we're going to interpolate to 0 in the corresponding boundary, right? So the function is 1 in here, and then it's 0 outside, and then I just interpolate linearly. If you look at it in the birth persistence or lifetime axis, it looks like this, right? So it's maybe a little bit easier to see. So again, it's 1 at the vertex, and then it's 0 outside, and you linearly interpolate. So these are called tent functions. So this is and by moving the center, you get several templates. This is another type of function. These are called interpolating polynomials. They're a little bit more complicated, but they also give you functions on the birth lifetime plane. So here's the theorem that one can prove with these template functions. So if you start with a collection of persistence diagrams, and the collection is going to be compact. So this is just a technical term saying that that this set is not too big in extension. And if you have a continuous function f from your collection of diagrams to the real numbers, so think of this as the ground truth that is going to tell you whether a diagram is either blue or red, then the following is true. Then for any epsilon, which is going to be sort of our degree of approximation, for any epsilon, one can find template functions f1 through fn, so that the following is true. You can also find a polynomial on n variables. So the number of variables is going to be equal to the number of template functions that you can find. And then the following is true. For each one of these functions, so f1, f2, fn, you can define these, remember these functions nu f1, nu f2, and all the way up to nu fn. And then what the nu f's are doing is, again, taking the points in the diagram and evaluating them on f, and then adding all the values together. So this is a real number right here. And then nu f2 gives you another real number, and all the way up to nu fn, that gives you another real number. So you get these n real numbers, and then you can plug them into this polynomial p, which has degree n, which has n variables, right? So this now gives you a number. And then what the theorem says is that the value that you get out of these process is very, very close to the value from the function f that you wanted to learn in the first place, right? So it's saying that the difference between this and this value is less than epsilon. So what are the challenges here? The challenge of this theorem is that it doesn't tell you what the template functions are. It just tells you that they exist, that it is possible to find them. And it also doesn't tell you what the polynomial is. But there are sort of two things that one can try to do. One can try to learn the templates by trying to by taking, for example, interpolating polynomials, or something like a tent function, like the ones that I showed you before. Take a bunch of them, and then to learn the polynomial, perhaps you just have to learn the coefficients, which is a typical problem in machine learning. So here are some experiments showing how this theory can be used in real applications. So here's an experiment where I have a bunch of spaces. So I have here a torus. So the colors are representing the z coordinate. So this is a torus, a circle with noise, a square, 3 clusters, three clusters of three clusters, and then right, these right here is a sphere, a two-dimensional sphere. And then from each manifold or from each space, one samples points. Like in here, we have a sample of the torus, and we compute persistence diagrams. Okay, and then the goal is to try to classify or to predict the manifold that we have from the observed persistence diagrams. So here's an example using the number of features. For example, we have 10 diagrams, we have 10 manifolds per class, sorry, 10 samples per manifold class, right? So 10 diagrams, 10 diagrams, we have 6 classes, so we have a total of 60 diagrams that we can learn from them. And here are the training and testing accuracies using 10 functions, right? So high classification accuracy from the persistence diagrams. Here's another example, the Rossler attractor. So what one does is it takes the system of differential equations and it simulates a solution. And then depending on the coefficients, A, B, and C, it'll give you a different point cloud. So for some choice of A, B, and C, it gives you a point cloud that looks like the cycle on the left. And then for another choice of variables, for values A, B, and C, you get a point cloud like the one on the right. And then the goal is to try to learn whether we are in these setting by computing the persistence diagrams of this point cloud, or whether we're in this setting by computing the persistence diagrams of these point clouds. So this is what is called a chaotic system, the one on the right, and this is a periodic system on the left. So here is the classification results. In the the diamonds and the pink circles are places where the algorithm failed to classify, right? So these are places where the algorithm thought that it was one of the classes. For example, it thought it was chaotic, but it turned out to be periodic, or the other way around. And it happens exactly where the system changes stages, right? So right here, these are boundaries between the two types of behavior. So these are reasonable places where the system will make errors, or the classification system will make errors. Another application is to the problem of chatter detection in machining and industrial manufacturing. So the problem of chatter, what it is that you have a piece of metal, a very sharp piece of metal that is cutting against an input piece of metal, and you want to sort of fabricate through this process, fabricate pieces through this process. If the cutting piece starts to undulate, that causes something called chatter, and it can damage the metal piece that you're trying to fabricate. So here's a sort of a classification accuracy plot of using sort of the time series of undulation of the cutting piece, and whether it is in chatter or not chatter states. And then the line in gray is the boundary between the chatter and not chatter regions. And then the red cross means success, that the classification of the system was correct using persistence diagrams. And then the blue dots is failure. And then the failure happens as it would be expected in the boundary between the two states. Here's yet another example where we take the Kuramoto-Sivashinsky system, and it produces images like the ones we're seeing on the bottom left. And then the goal is to try to learn sort of what type of constants were used, in this case R, what types of constants were used to produce the different regimes of the system. And here's some results that show that one can classify very accurately what the state of the system is using these images, which one then turns into persistence diagrams. So going back to the problem of choosing the template functions, right? Because we said that the theorem does tell you that, there exist some templates, but it doesn't tell you how to choose them. So here's a paper describing how to find the templates adaptively. So as we said before, here on the left-hand side is a picture with several persistence diagrams colored by their class. Then what one can do is one can use the class and adaptive methods to try to sort of estimate the domains or the regions where we're going to put the templates, right? So some of the results that one can obtain with these methods are going to be described next. So going back to the data set of poses, here's a table showing the results of using different featurization methods, which are adaptive and non-adaptive. So here are the polynomial, the interpolating polynomials, meaning that, again, these are the template functions we're using. We're interpolating polynomials. We get something like, let's say, like 92% accuracy, 95, 93. Using 10 functions gives you, of course, in this case, worse accuracy. And then adaptive templates gives you something on par with the interpolating polynomial features. The thing to notice is that the adaptive method gives you local features, just like 10 functions do, but with accuracy that is on par with the interpolating polynomials and with smaller variance in classification accuracy. And then to finish, going back to the protein classification benchmark dataset, again, one computes persistence diagrams and one can compute classification accuracy using this adaptive template functions. And then what one can show is that one can obtain sort of classification accuracies of, up to 98%, which is an improvement from an 82% classification accuracy using hand-picked topological features in a previous study. So to summarize, in this lecture, we've explored several methods for doing machine learning with persistence diagrams. The idea is that if your data set is comprised of objects which themselves have geometric features, then one can capture those geometric features using, for example, persistence diagrams. And then the goal is to apply machine learning methods to features obtained from the persistence diagrams. Thank you very much.